Hello, my name is Leah Dierker Viik. In this presentation, I will describe Structural Component 6, which is a computational tool to make the conceptual design of buildings easier. Here is some contact information in case you'd like to learn more about this project. So, the building industry has historically been very inefficient and wasteful. This is demonstrated by the MACLEAMY curve, which you see here. According to the MACLEAMY curve, the bulk of work done in the traditional architecture or design process occurs too late when many of the key details of the design have already been consolidated. To avoid this problem, the bulk of work should ideally be shifted earlier in the conceptual design phase. But the question really is, how can we provide engineers and architects with enough information to work effectively in the conceptual design phase? This brings us to the project Structural Components. This is an ongoing project within the Delft University of Technology and Lioness Technologies, which is focused on improving the conceptual design of buildings. So far, there have been 5 previous iterations. You can see one of the iterations here. This presentation focuses on the most recent iteration, which is Structural Component 6. This tool focuses specifically on mid-rise concrete buildings laterally supported by shear walls and cores, which are referred to from this point as stability elements. In this tool, a user can construct and validate a conceptual design with a flexible number of stability elements on a floor plan. It is assumed that the stability elements behave like flexural beams, which are connected together by infinitely rigid floors. The tool analyzes prismatic buildings, that is, buildings with a uniform cross-section from base to top. After the user has constructed their conceptual design, they can apply loads to their building, and the tool will calculate the forces and deflections in response. The tool will also check these forces and deflections against Eurocode standards and let the user know if their building is adequate for these standards. Now I'll describe a little bit about the background of the calculation method that I use for this tool. So in order to analyze buildings with a varying number and arrangement of stability elements, I had to first develop a calculation method to do this. In order to test my calculation method and the assumptions that I made, I analyzed 3 different floor plan configurations that you can see here in the slide at the bottom. After analyzing the 3 configurations, I found the following results. Deflection, shear force, and bending moment were very well predicted by this rigid floor method, and the accuracy became better as the floors became thinner. However, torsion around the core from test configuration 2 was very badly predicted. But I compared the torsional stresses against the bending stresses, and I found that the torsional stresses were much lower than the bending stresses. In conclusion, I determined that the calculation method should be applied to prismatic mid-rise buildings with hinged floors, but that torsion should be omitted. These results led to the following calculation method. Here you see a system of 3 equations representing the force and bending moment equilibrium of a given floor plan. The system of equations is flexible and can grow and shrink depending on the number of stability elements on the floor plan. This calculation also uses the following boundary conditions, which in essence state that the building is fixed in both translation rotation at the base and free at the top. Now I'll describe the development of the tool itself. Structural Component 6 was developed in Grasshopper, and the calculation method was written in Python with Grasshopper's Python script component. 4 Grasshopper components were developed, as you see below. 2 to allow the user to construct their floor plan. 1, a calculator to allow the user to apply loads and calculate the responses. And finally, a visualizer, which allows the user to see their building and provides feedback on validation checks. So here you can see how the user would construct their model in Structural Component 6. First, they create however many stability elements they would like in a floor. Then they put their model into the calculator and apply some loads. And finally, they put output from the calculator into the visualizer, which you can see on the right visualizes the building and provides feedback if one of the validation checks fails. Here you see that a wall turns red if it fails a particular validation check. So to test how well this tool could work in practice, I wanted to test it on a real building. The building you see at the left here is the electrical engineering building at the Delft University of Technology. The floor plan you see on the top right of this image is the actual floor plan of the building. However, I modified this to the floor plan you see below, since the shape of the floor itself does not actually affect my calculation method, only the stability elements matters. So here you can see what this case study actually looked like when I put it into the tool. So at the conclusion of my case study, I discovered that all of my structural validation checks failed. There are a few possible explanations for this. One, the structural system was greatly simplified in my analysis. Two, the foundation stiffness used in the calculation may have been much too low. And three, building standards are much stricter now than they used to be. However, by putting this building into the tool, I did show that this tool could be effectively applied to a building with a large number and complex arrangement of stability elements. So this finally brings us to the conclusions of the project. So I determined that the calculation method that I made is generally applicable for prismatic mid-rise concrete buildings with precast or hinged floors. However, it is very limited in its ability to analyze torsion. Through the case study, I found that the tool can be successfully applied to a building with a complex arrangement of shear walls. I have some ideas for future recommendations. Very important to investigate the effects of torsion and also out-of-plane floor effects on building behavior. I would also like to investigate the addition of expansion joints in the floors because these are very common in buildings. It would also be useful to add more stability elements to the tool and also to allow the user to add non-rectangular floors because this gives more flexibility from an architectural standpoint. And that brings me to the end of my presentation. Thank you very much for listening.